Hello everyone, my name is Nathan Streck, and in this video I'm going to be presenting a new physics theory. It's something I call Anaglyph Theory, and like the title suggests, I'm going to be talking about quantum information and how that information combined with the geometry of space-time defines our physical reality. But before I get started, a quick disclaimer. I just want to make it very clear that I'm not a physicist, I'm not a mathematician, I'm just a science enthusiast with a fun theory to share. So if you're the type of person who enjoys listening to new and creative, maybe very far-reaching science theories, then I think you're going to enjoy this video. So let's get started. And we'll get started with a quick history lesson. So in physics, there have been two great unifiers throughout history, and the first one being Isaac Newton, who we're all familiar with. And in the 17th century, Newton helped unify the forces of gravity here on Earth, like a force of gravitation on a falling apple, with the forces in outer space, like the forces that hold the planets in orbit. So then the next great unifier was James Clerk Maxwell, who following in the footsteps of the great Michael Faraday, who was the great experimentalist, and he did a lot of experiments with electricity and magnetism, and he documented all of that very well. James Clerk Maxwell took those results and mathematically unified electricity and magnetism, and he showed the world that they're one and the same. And today we call that electromagnetism. So what's the third great unification? Well, historically, that is the unification of electricity and gravity. And that story dates back to, again, Michael Faraday, the same guy working on electricity and magnetism. Around 1850, Michael Faraday was working on experiments to find the connection between electricity and gravity. And while his experiments didn't help him find any evidence, up until his death, Faraday remained convinced that there was a connection between these two things. Now, the next person to pick up this task was Einstein. So Einstein, starting around 1923, really started to focus on a unification between electricity and gravity. But at this time, now it's called electromagnetism and general relativity, his general relativity. So he worked on that problem up until his death until 1955. Now, I've already given you fair warning that this is going to be a very far-reaching new physics theory. So this is me here, Nate, and in this talk I'm going to be presenting my solution to the third great unification. I'm going to show you that using quantum information, you're able to put gravity, electromagnetism, and even thermodynamics together within the same mathematical framework. Okay, just to give you an idea of where this talk is going, I want to present some of the mathematical conclusions, some of these equations that pop out of that framework that I've mentioned. So just to start here at the top, physics in general, in a very generic sense, is centered around describing actions. And in the year 1900, a scientist named Max Planck started quantum theory by introducing what he called a quantum of action. Now today we just call quantum of action Planck's constant, and that's represented by the lowercase letter h. So this is a very fundamental physical constant of the universe. It's very much part of the foundation of quantum mechanics. And in this talk, I'm going to show you how to define other properties of the universe, such as entropy, temperature, and gravity, within the context of quantum mechanics. Just like we already have a quantum of action, we're now going to have a quantum of entropy, temperature, and a quantum gravity. Now, you might say, hold on, don't we already have equations for entropy and temperature and gravity? And to that, I would say, no, you really don't. The equations that you're familiar with today only define these as proportionality constants. So for example, down here in the lower right, we have a simple equation that states energy is equal to Boltzmann's constant, which is related to entropy, times temperature. So, if we were to take away temperature out of this equation, Boltzmann's constant wouldn't really make sense at all. It is just a proportional value to relate other values. And similarly with Newton's constant, or gravity, or usually just called big G down here, this is a proportionality constant that connects the force of gravity with two masses and the inverse square of their distance. So you can see, if we take away these masses, this gravity really doesn't make sense in this context. So again, these are just proportions. But up here, my new equations, these are the explicit definitions. These are the essence of what they are. It's the core description at the quantum mechanical level. And I'm very confident by the end of this talk, you're going to clearly see where these come from. If there was one physicist that was central to my theory here, it would certainly be John Archibald Wheeler. Wheeler is a very famous American theoretical physicist who worked, in the theoretical development of the atomic bomb. Wheeler studied under Bohr, and he often conversed with Einstein. He helped mentor the famous physicist Richard Feynman. And Wheeler is also known for popularizing many terms, such as black hole, wormhole, quantum foam, and another one, just it from bit. And this is the one we're going to focus on for this theory. So it from bit is Wheeler's way of saying that all physical things may be manifested or created by quantum information, or just bits. So that is really the core of this theory, and we're going to be diving into that a lot more. But John Wheeler spent most of his career at Princeton, and during this time he supervised more PhD students than any other physics professor. And I already mentioned Richard Feynman, but many famous physicists came out of Wheeler's doctorate program, including Jacob Bekenstein. Bekenstein was a very famous Israeli theoretical physicist who gained his PhD under Wheeler in 1972. Now, Bekenstein is probably most well known for his argument with Stephen Hawking. Now, in a very brief summary, what that argument was about entropy. Now, Stephen Hawking originally showed the world that if you throw something in a black hole, the size of the area of a black hole will increase. The surface area, the event horizon of a black hole will increase. And Bekenstein argued that in addition to the surface area increasing, the entropy must increase. So the entropy is tied to the area, the surface area of a black hole. And Hawking wasn't buying that originally. But after some calculations and some thought, Hawking came to agree with Bekenstein and helped him revise his mathematics and became, the champion, along with Bekenstein, of proving that black holes actually follow the laws of thermodynamics. So he was instrumental of our understanding of black holes as they are today. And one equation that Bekenstein was famous for, or really famous for, is called the Bekenstein bound. Now, this formula is used to calculate how much information is in a given region of space. Now, looking quickly at this equation, we've been talking about action, which is sometimes represented by the capital letter S. But this capital letter S is for entropy. So this is really a definite. The Bekenstein bound is considered an upper limit of something called Shannon entropy. And Shannon entropy is defined as a measure of information in a system. So a way to use this equation in the real world would be to describe the amount of information contained on the surface area of an event horizon of a black hole. I know that's a lot. But in a sense, you could put in the radius of a black hole and its total energy, and it would give you kind of an idea of the information content stored on the surface of that black hole. It is a pretty strange concept if you're not familiar with it, but in quantum mechanical and information terms, strictly in the terms of bits, the Bekenstein bound is given in this particular format, where this lowercase letter I that I'm using is just expressed in the number of bits in the quantum state. And then we have this new natural log of 2 factor that comes from being spread across the different quantum states. And, for all fundamental particles, it turns out that the number of bits come out to be 9.06 bits. And yes, you can think of these as ones and zeros, like bits in a computer, but I don't think nature, uses ones and zeros. It uses the growth and decay rather than a 1 and a 0. So that's where you might just be surprised that it's not an integer value like a normal bit that you're familiar with. This is something a little bit different, but it could still be represented as bits. And the way I got this number is I'm doing a quick calculation here by putting in the Planck length, the Planck energy in for these values. And it turns out that when you do this, the length and energy cancel out with h bar c down here. And you're just left with this simple expression that of 2 pi over the natural log of 2. So I know this is, again, very strange new concept, but this is well-known physics. And even if you replace these, kind of vague Planck values, you can put in real values of a fundamental particle, such as an electron. If you were to redo this calculation with the mass of an electron and its reduced Compton wavelength of an electron, you would come out with the same value of 9.06 bits. So in a way, what I'm really saying is that this is the smallest amount of bits that can describe a fundamental particle. And for the rest of this talk, I'm just going to consider this to be the quantum of information. The smallest packet of information in the universe contains just over 9 bits. So just keep that in mind, and you'll see how it comes into play in a little bit. I've already mentioned Max Planck a couple times, and I mentioned that he was the originator of quantum theory and that he helped us define a quantum of action that we now call Planck's constant. But a quick fun fact about Planck, he was a gifted musician. I didn't know that he was a singer and he played so many instruments. I thought that was pretty neat. But another thing that Planck is famous for are his set of natural units. These are the Planck units, and the way they work is Max Planck chose 5 constants in nature that we're able to measure. And, if you combine these constants in just the right way, the units will cancel out and you'll just be left with particular units, like meters in this instance. So a Planck length can be defined by Planck's constant, or reduced Planck's constant, times by gravity, divided by the speed of light cubed, all squared, and that'll give you a very, very, very small length in meters. And the same can be done with time and mass. So the key here is that we can come up with these units, such as length and time, without any human-defined reference points. This is almost natural, a natural unit system. So the first physicist to really find realize the importance of Planck units was Arthur Eddington. But John Wheeler was really the champion that helped popularize the Planck units in the 1950s. He was the first one to introduce the idea that gravity and quantum mechanics kind of come into play and interact at these scales. Now, finally, I can start introducing some new content related to my theory. And the first thing I'm going to introduce are my new set of natural units. I call them the Wheeler units, and you can see them here compared next to the Planck units. And just to be very clear, these are my natural units that I created. They have nothing to do with John Wheeler. So I hope that they're right, and I'm not just dragging his name through the dirt. But just a couple quick observations right out of the gate. You can, just looking at the mathematics, looking at a Wheeler length, that's what this W is, just stands for Wheeler, and this Planck length over here is LP. But just looking at Wheeler length and Wheeler time, you see that it's just simpler than a Planck length and time. So usually in physics, simpler is a good thing, but not always. So I think that's kind of neat. And then the second thing to notice right away is that there's a difference in the base units of charge. Now, the Wheeler charge actually uses elementary charge, which is the charge of an electron, the smallest charge we can measure in nature. It's a tangible, it's a real thing that we can measure, and it's a quantity that we use. And you'll see that the Wheeler units actually use that base charge, as opposed to the Planck charge. Planck charge is kind of like, well, I don't know what it is. I find it a very fascinating number for many different reasons, but it has nothing to do with the real charge value that we find in nature. And I can translate that into Wheeler units. You can see we just divide elementary charge by the square root of the fine structure constant, which is also known as Sommerfeld's constant, and we can get the same value. But I just want to make sure it's clear that, there's two different charges here. Now, I think one of the most important things when creating symmetrical units is selecting the right constants. And, we're using 5 different constants up here, and Planck made his selection, his lineup, and I've made mine. And I think it's very important to select the most fundamental, the correct units in order to see the correct view of the universe. And I'm going to tell you why I picked these constants. So really quick, we've mentioned Planck's constant a couple times, but physicists will refer to both of these as Planck's constant. There's one called h bar with a little bar over it, which is sometimes called the reduced Planck's constant or the Dirac constant. But the original Planck's constant is just the lowercase h. So physicists will use these interchangeably and just call them Planck constant, and they're only separated by this value of 2 pi. So just be aware of that. I'll probably call them both the Planck constant too. So looking at the Planck's constant, I told you that it's one of the foundations of quantum mechanics. It's one of the essential quantum mechanical variables that there are. But what I've done is I'm taking all of the quantum mechanical pieces that make that up, and I'm calling those more fundamental than Planck's constant. I mean, that kind of makes sense, right? These are what make it up, so they have to be more fundamental than Planck's constant itself. And in addition to that, I'm adding a little bit of quantum information, and we already talked about that with this is the Bekenstein limit, or the quantum limit of the Bekenstein bound. And John Wheeler's quote from his autobiography that I've included here says, information may not just be what we learn about the world, it may be what makes the world. The next interesting thing is that the Planck units and the Wheeler units have the same values, the same outcome. And, knowing that we're using different constants to create them is pretty amazing. So I certainly don't think this is coincidental. I think we're defining the same values, just looking at them through a different lens. So I think that was pretty darn interesting. And then the next thing is the unit of temperature I quickly want to talk about. Now, I mentioned early on that our understanding of temperature today really depends on multiple particles. It is a proportionality value. And we define that or explain that using a unit, a Kelvin, capital K. But in Wheeler units, at the more fundamental level, we don't need that anymore. These units are worked out to be charge times acceleration. That's what this big C is over here. This stands for a coulomb. A coulomb is a unit of charge, and then we have a meter over second squared. So that's an acceleration times a charge. And you can see that over here in this equation. And so we're really going from, our understanding of multiple particles describing temperature to a single particle that can now describe temperature. So you can see that I believe the Wheeler units are more fundamental, and we can define the exact quantities a little bit better. Now, this is a little strange. This is not part of Planck units. This is something new that arises from that equation for Boltzmann's constant that I introduced a little bit earlier. Now that I've presented this equation, we can rewrite the quantity of elementary charge in terms of Planck units. So this is something new that is not known yet, but I'm proposing this new equation of simply elementary charge equals Planck's constant over Boltzmann's constant times the speed of light. Now, quick fun fact about this equation that I find really fascinating is that physicists will know that this Boltzmann's constant, this K, was not created by Ludwig Boltzmann. It was named after him. The man who created this constant was actually Max Planck. So Max Planck created both this H and this K. And it just really boils down to a very simple equation that, again, if what I'm saying is right, I'd feel sad that Max Planck didn't get to see this. Now, finally, again, here's the two units side by side. But, in addition to your base units, what units allow you to do is to derive other units, such as force, energy, momentum, stress, pressure, all the different properties of the universe can be expressed by simply using or combining the base units. And, using the base units, you can get everything else. And that's what I was showing you in the beginning. You can see, again, the Planck's constant, Boltzmann, and Newton's constant that I described earlier. And this is what I mean by putting them in the same framework. You're unable to put these things in the same framework in Planck's units because I think he's using this wonky charge value. It's not right. But, once you get the right constants defined and everything lined up correctly, everything makes sense together. Now here's even a longer list of Wheeler units. These are a huge list of, not huge, this is actually a portion of all of the derived units that I could present, but this is a mixture of derived units and base units on a single list. I have them organized from big values down to low values. And I've just been calling them properties. I really don't know what these things are called. Do you call them attributes of the universe, different phenomenon? So I'm just going to continue to call these different things properties as I go forward. But the way I like to think of them is just things we've learned how to measure. I mean, I wouldn't put too much value in your understanding or your fundamental, understanding of these different things. Just know that they're different things that we know how to measure. Now, if you're still with me, we've finally got to the fun part. So we're going to start to see pictures, a lot more pictures to describe things. Now, the picture on the right here is called a stereogram or a stereoscopic image. And it's a special kind of image that will help trick your brain into seeing a 3D shape. And to be specific, this truncated icosahedron is the shape that's hiding in here. And I really can't help you see that one. You'll have to figure that out on your own. But in kind of a similar way, the Wheeler units are hiding an image as well. They're hiding this hyperboloid type image. And for the rest of the talk, I'm going to show you how that image pops out of these properties. This list of properties will generate an image that looks similar to this. And to do that, I'm going to have to show you how to interpret the Wheeler units, how to read them correctly. And to do that, I separate them into three separate columns. And you can see here that there's the Wheeler length, which we looked at before, is simply I/E over c squared. And that's what we have over here, I/E over c squared. It's the same equation. I've just stretched it out over three different columns. So the next thing I'm going to do is describe to you what each column does. And then as we go along, you'll start to see the picture I keep talking about. So starting with column 2, it defines the layers of things. And spoiler alert, there are going to be different layers at the quantum scale, different mirror universes, if you will, at the very small scales. And we live among both of those mirrored universes. We kind of are a product of multiple layers. And that's what layer 2 is showing us. If we sort all of the properties over here, if you remember, I previously had them sorted, big value to small value, which didn't really tell us much information. But now I've sorted the properties according to the second column. And what that does is it sorts them into their appropriate layer where they belong. So what the heck do I mean by different layers? I'm going to show you 3 different hints that there might be some microscopic different layers, to our reality. And the first one is with James Clerk Maxwell again, the guy who unified electromagnetism or electricity and magnetism. One of the things he did is, while he was unifying electromagnetism, he realized that light, the speed of light, or visible light, was also an electromagnetic wave, and he knew that because the speed that he calculated came out to be the same as the speed of light. And this is the equation for the speed of light that he came up with, which is basically permeability and permittivity, the inverse of the square root of those two. So it's basically saying that there's a magnetic constant and an electric constant kind of help define the speed of light. And the way the speed of light works is, I think it's just a oscillation in the magnetic and the electric fields. So if the magnetic field has a wave, it'll affect the electric field. And if the electric field has a wave, it affects the magnetic wave, and vice versa. It goes back and forth. So there's an oscillation. Light is oscillating between electricity and magnetism. That's what an electromagnetic wave is. And it travels at the speed of light. So we can see that both of those values are on, different layers. And right in the middle of that is the speed of light. So that's our first clue that there might be 2 parallel universes very, very, very close to each other. The second clue is that I'm going to point out is a simple electronic circuit. It's called an LC circuit. And in this circuit, L stands for the inductor, which is just a coil of wire. And C stands for the capacitor, which is just 2 conducting plates separated by a air gap, if you will. And so this is one of the simplest electronic circuits you can make. And if you were to put electricity into this circuit, it would resonate. It would actually take the electricity and put it here in the capacitor. It would store electrical energy, and then that would send it back to the inductor. And the inductor would store it as magnetic energy, and vice versa. That energy would resonate between those 2 components. That's what this picture is down here. This is a very, very large Tesla coil that I found online. But that's what you're looking at. This circuit here is identical to this here. This long post, or this tower, is actually the solenoid, this blue thing. And then the capacitor is actually represented by this topolo, this donut shape at the top represents this top of the red plate. The bottom of the red plate is actually the ground, or this pole sitting on the ground. So this gap in this air right here is actually a representation of this gap between this capacitor. So that's just a nice visual way to see a LC circuit in action. But that's our second hint that there's some sort of communication going back on these. This first one was oscillating. The second one is resonating. And the third one is communicating. So John Wheeler tells us that space and time, or space-time, tells matter how to move, and matter tells space-time how to curve. So we can see that mass and energy, not just mass and energy, anything with energy will react with gravity. But you can see that, just to recap, we have all these different layers communicating with each other. They're either oscillating, they're resonating, they're communicating, and I'm making the argument that this is just information being passed back and forth. They're still talking to each other somehow between the layers. So right now, probably sounding a little crazy saying that we live among parallel universes at the quantum scale. But I just want to take a moment to show you that scale, what I'm talking about. So here's a quick scale of things. You are here. This is, from 1 meter to 2 meters. That's probably how tall you are. This is where you're at on the scale. And going all the way to the right would be to the size of the observable universe. And all the way to the left would be down to the Planck scale or the Wheeler scale, either one. But Wheeler actually called this scale down here the quantum foam because we have, virtual particles popping in and out of existence and weird things happening. But this is the scale I'm talking about here. This is where the two parallel universes that I mentioned exist, way down here at this space-time scale. And you can see it's way smaller than what we work with at the Large Hadron Collider and at CERN there. So it's just far smaller than anything humans can see today. One interesting thing about this scale that I always think is curious is that, again, you are here, and you are closer to the size of the observable universe than you are to the size of space and time. So the world of the small is actually smaller than the world of the big. I like to think about that. So now that I've proposed that there's different, layers with column 2, we're going to take a look at column 3. This is my favorite column. This is where it gets really fun. So column 3 is constructed of two things. It has an elementary charge, and a velocity. And you can see over here, I've kept the highlighted colors of the layers, but now I'm highlighting column 3, and we're going to take a look at how that works. It's called position or layer position. And this one's fun because I treat it like a little board game. I think you should definitely learn the rules. It'll help you in physics, even if my theory is wrong. I think this is a helpful tool. But the board game is similar to chess. It's nothing like chess, but similar in a way. And the board is actually space and time. And you see this X axis is space. And when I say that, this is, spatial dimensions. And then we have time. And I'm not traditionally, time goes positive in a space-time diagram, but just be aware that I'm using minus time to go into a vertical direction here. And the first playing piece is the velocity, a speed of light. And we know the speed of light is, measured in meters per second. So that's a length over time. And so you can see it's where it belongs. This is a length over time. And again, we're going negative, so over time. So the speed of light, this is its starting point. And in a strange way, this piece can move. It can move, over one and up one, over one and up one. So it moves along this diagonal, kind of like a bishop in chess. But it can only move in this diagonal. It can't go the other way. So that's the first playing piece, is the velocity. The second playing piece in space-time is charge. Charge with the little e here is located, you'll just have to trust me on this one for now, but it is located at a dimension of 3 lengths, which would be a volume, and over 2 times. So that would be angular acceleration, which just means a rotation. So in a weird way, this is just a volume that's rotating. And just remember that over 3 up 2 is a charge. That's an important square. And I would say this playing piece behaves similar to a knight, but it can jump 3 squares over 3 and up 2, or down to over 3. And that's the only move it has. It can move down 2 this way and over 3 this way, but it can only go in this position. So these are the first 2 playing pieces that we start with, but then we can build the other ones. And what I mean by that is, let's look at the simple ones, length and time. Now again, with these first 2 playing pieces, we could start to construct the rest. So looking at length, we start at E, and that's divided by 2 speed of lights, c squared. So if we start at E, we just go down to over 1 down, another down, another 1. So you can see we just went down 2 speed of lights. And that brings us here to this location. And that is a length, and that lines up with our chart, our grid. We are at 1 length and 0 time. And then you should be able to figure out the time is, figured out the same way. We start with E, and we go down the speed of light 3 times, and we find ourselves at positive time. So that's the way the board game works. And now that you understand the rules of the game, we can start to lay out the full board game itself. So remember, there were 3 layers, and now I've just zoomed into the top layer, the blue layer, and we're looking still at column 3 of this top layer. And we play the game with each one of these little properties. So remember that the charge E was over 3 up 2. And we can easily see that where mass lives on this top layer. So that's an easy one. And then energy is just charge times c squared. So again, we would go to where charge lives and then go up 2 speed of lights, and we get up here to energy. So you can see how every one of these properties has a unique position on each layer. So this is the top layer and all of the properties. Not all of them, I'm just showing you a select few, but generally they seem to, I guess, coalesce along this vertical line between space and time. And then quickly looking at the middle layer, this is where the properties of the middle layer live. And this is the one we already did the training on. Remember, the charge was here, and we looked at length and time. But 1 over time would be a frequency, and you can see we go into the negative direction here. So that's all of the properties on the middle layer. And a really quick note here, though. I don't think the middle layer is really a layer. It behaves like a layer, but it is something different, and it's sandwiched between the top layer, the blue layer, and the bottom red layer. So just keep that in mind. But then finally, to finish up this point, the bottom layer has 3 playing pieces, but you'll note that permittivity, or electric constant, and gravity, they don't have a position. They're blank. I actually believe that that means they exist on the entire plane, the entire layer. I've just put permittivity here at position 0, 0 for clarity later. But again, I don't think gravity has a position like everything else. And now we can start to play the game. So what we're looking at here is a top-down view of just the top layer and the middle layer. And you can see I didn't change anything. The positions and the layers remain fixed. They're always fixed. They don't change. But what I've done is I've cut away a piece of the top layer just so you can see underneath it. Otherwise, it would just be a big blue sheet here, and we couldn't see the middle layer underneath it. So here are some smart people that have played the game before you, and we can see how they've played the game. So just really quick, here we have Isaac Newton, we have Max Planck, well, I think it's pronounced Planck, but I'm going to keep saying Planck. And then we have Albert Einstein and Louis de Broglie. These are some smart guys that have learned the rules of this game. So we're going to start by looking at Isaac Newton's famous equation, F equals ma. And let's just look at combining m and a. Now, one interesting thing is all the multiplication turns into addition, and all the division turns into subtraction. So things actually become simpler in higher dimensions. But again, looking at F equals ma, we're going to add mass and acceleration together. So where's acceleration? It's over here. Acceleration is over 1 up 2, or meters per second squared. That's what acceleration is, but over 1 up 2. So then if we go to mass, and we go over 1 up 2, we're going to find ourselves at force. See how easy this game is? It wasn't too complicated. But then looking at the next one is energy equals Planck's constant times a frequency. And of course, here's Planck's constant. And we're going to, instead of multiply, we're just going to add a frequency. And the frequency is over here, which is a minus time. So h plus a frequency gets us to energy. I think you get how the game is played, but we'll continue to look at a few more. Einstein's is pretty easy. We already did this one. We have a mass right here, and we add 2 speed of lights, 1 2. We get energy. So that's not really that impressive. And once you see how it's all put together, we can build equations just like the best of them. And then finally, just to finish the point, we have Louis de Broglie, who this is a lambda. This is a length, a wavelength. So it's saying a length is equal to h minus p. Or another way to say it is just a p plus a length, and you get to Planck's constant. So that's it. It's a very simple game that is easy to play. But now I will take a look at what I would say level 2 of the board game. We can do the same thing. We're still looking top down, but we're taking different cutaways. See, the blue layer is the top, the beige or the light orange is the middle, and then there's red is the bottom layer. And what I've done is just strategically cut out pieces so you can see what I wanted you to see for the time being. And right now we're looking, straight down through all the layers, and this particular view is going to help us see electromagnetism and what it is. And here are some, very simple, popular electromagnetic equations you would find in a simple science book. And I'll let you do all of those. They work the same exact way, but we'll point out this one. We'll do this one together. So this is current equals voltage over resistance. So if we go to voltage, which is here, and we want to divide by resistance, which is over here, you think we would subtract it, but just note that resistance is flipped in science and time and space. So it's going to do opposite of what you think. So the voltage plus resistance would go up here to the current. So that one's just a little tricky one. But the rest are pretty straightforward, just like we did before. These tables will confirm or validate any physics equation that there is. Now, finally, we looked at the different layers. We looked at the properties, different layer positions. And then the final column, or column 1, is the information. Now, this is the information that is communicated or exchanged between the layers or staying on a layer in the case of temperature and entropy. It's a special case, but we're going to look at how that quantum information is exchanged between the layers and how they talk. And you can see I have column 1 highlighted here. And then again, here's that same old top-down view that we just looked at. But to see the information communicating between these layers, we need to rotate this on the side. So now we're looking at the side view. And the side view is going to allow us to see where gravity is hiding. Gravity is operating in a higher dimension. Now remember, each one of these sheets, or at least the blue and the red ones, are space-time sheets, different dimensions. These are mirror dimensions at that quantum scale. But at a different dimension, unknown to us, this bridge that connects them together is able to exchange information through it. And that's what we perceive as the force of gravity. It's gravity down here communicating up through this information bridge to other things up here. That's my claim. And how do I know this is gravity? Well, we can look at a few more examples. I have 4 more examples to look at. And starting with the top one, little m is mass. And divided by mass, I have some dimensions, length 3 over time 2. What that means is, remember that charge and mass, remember they were at length over 3 up 2. So that's where mass was. If we drop a thread, or I have like a picture of a ribbon here. If we drop this ribbon straight down to the bottom layer, this square right here is going to be a length 3 over 3 up 2, just like mass, because they stack on top of each other. So the dimensions down here, this length 3 over time 2, are this particular square right there. And if we divide mass by the square down there, we're going to find gravity. And you can put some values in there if you want. You could put a mass Planck and a Planck time and a cubed Planck length in there and do the calculation. You'll find 1 over big G. But the curious point is you could do that for everything else. So here's momentum, little p is the next example. Momentum is over 4 up 3. So if we were to drop a ribbon straight down to the bottom layer, we'd be hitting the same square, length 4 over time 3. And once again, you would find a value for Newton's constant, G. Same thing for Planck's constant. If we drop a ribbon down, we're going to hit the spot is over 5 up 3. And then finally, force, again, it's the exact same thing. If we drop a ribbon down from force to the bottom, we're going to hit length 4 over time 4, which is just speed of light to the power of 4. And this one's curiously just the same equation for Planck's force. So Planck force is equal to C4 over G. So that Planck got that one right. And I'd like to just pause for a second to see what we've done so far. So we've created a new set of natural units called the Wheeler units. And those are essentially just built upon 5 constants that are found in nature. One new constant that I'm proposing, which involves quantum information, but still the units are constructed of 5 values. And those 5 values allow us to manipulate it in the right way, allow us to build this picture that we're looking at here. I just think that's pretty amazing. And it leads me to believe that the units might be correct and I might be onto something. But before I really start to wrap it up, I want to talk about one last thing, and that's thermodynamics. Thermodynamics are really the foundation of physics, and it's really just based on the idea that energy cannot be created or destroyed. But specifically, I want to look at the second law, and the second law states that energy or heat divided by temperature is equal to entropy. Now, here's a picture of Arthur Eddington. He didn't create the laws of thermodynamics, but he once famously said that, if your theory goes against the second law, then you'll be humiliated, and I don't want to be. So let's take a quick closer look at the second law with relation to the Wheeler units. So again, we have energy divided by temperature equals entropy, or Boltzmann's constant in this case. So again, we can go straight down the columns. Column 1 would be 1 over I divided by 1 over 2 pi I. You'd have 2 pi. And obviously, Coulomb's constant divided by the fine structure constant divided by 1 is the same thing, and so on. These wouldn't be very good units if that didn't work. But of course, the values line up. But let's take a quick look at how the board game works for this one, or how the grid plays out. And I find it interesting that the positions and the layers that temperature and entropy take. Temperature actually is at length 4, time 4. Boltzmann's constant, or entropy, is curiously just at a length on the top layer. So that's kind of weird. But again, if we play the game, we see that energy divided by temperature gets us to Boltzmann's constant, or alternatively, just temperature plus Boltzmann's constant gets us to energy. So you see, the math works out, the board game kind of checks out, and then one other point that I find curious here is I mentioned that temperature is at the space 4 on the middle layer. But on the top layer, if I were to fill in the top layer here with blue, we would see that force is right here. So force and temperature are somewhat related in the fact that they have the same position, but they're different layers. So that's very curious to me for different reasons that I won't get into. But and then finally, just one last look at this is Stephen Hawking's equation. This is the Hawking temperature of a black hole, and it is presented right here. It's h bar times the speed of light cubed divided by 8 pi times Newton's constant times the mass of a black hole times Boltzmann's constant. So if we were to add the numerator up, if we had h bar, or h, which would be, it was over 5 up 3. This is where h resides on the top layer on blue. So if we have it at 5.3 already, and we add 3 speeds of light, you'll see, these combined become the over 8 up 6. And similarly, if you add up like the values on the board game on the bottom, you're gonna get these values. And then if we subtract them, 8 minus 4, we'll get 4. So you see that the temperature, a Hawking temperature of a black hole, has the correct dimensions that we proposed. So that checks out. That's a good thing. And of course, this is the Hawking temperature, the famous equation that's his epitaph on his tombstone here. And I just find it interesting that, I know in a sense we're just doing dimensional analysis, but if you really memorize that grid or the board game, as I say, you'll be able to see an equation like this and just instantly say, yeah, that's legit or not. So I think there is some value to memorizing the little board game if my theory is right or wrong. I mean, before I started working on this, I would have no clue if this is accurate or not. But now I can just glance at it and say, yep, that's legit. And now I must point out the bad news. So there's a small discrepancy between my theory and what we see in reality. These are measured values or experimental values, or I should even say empirical values that we measure in laboratories. There's actually specialized physical equipment to make these measurements. And these are very difficult measurements. If you see the scientific notation here, this means that there's 22 zeros in front of this one. So it'd be 0.000000, 22 zeros before you even reach this one. And with gravity, there would be 10 zeros before this 6. So these are extremely small numbers, and they're notoriously difficult to measure. Well, at least gravity is. But you can see the percent error between my theoretical values and what we measure in the real world are both less than 1%. So, I mean, yes, that's a lot for, physics. That's a big discrepancy. But, we saw this beautiful grid, this structure that kind of answers all the equations and predicts everything correctly. It just seems like maybe they measured those wrong, but I really don't know. And then now we're getting into the conclusion part where I'm proposing that this hyperboloid picture that was supposed to pop out of the Wheeler units looks something like this. At least in my mind it does. So we have, two identical sheets of space-time that are connected by an information bridge. And I think that bridge is, similar to a charged particle because looking at mass, we have the charged particle and mass kind of exist along that same bridge right there for some reason. I don't fully understand it, but it's just curious that mass and charge kind of live right here on that bridge. And if you're not up on your history of physics, most physicists would know this paper by the name, the ER paper. I've highlighted the names of the people, Einstein and Nathan Rosen. So the ER paper is a solution to Einstein's laws of general relativity, because he wrote this paper 20 years after he developed general relativity. So we know it's a valid solution. But what Einstein is saying in this solution is that there are two identical sheets of space that are connected together by a bridge. And he proposes, again, in this paper that this is a particle, very similar to what I was proposing. So that's one curiosity. But John Wheeler came along and he named that bridge the wormhole. So that's how we know of the Einstein-Rosen bridge today is called a wormhole. And I've scanned this paper out of Wheeler's autobiography. But again, in his chapter on gravity, he's talking about how he envisioned a space riddled with a bunch of wormholes, and that resembled an electric charged particle. So we're all kind of saying the same thing here. And Wheeler even finished his thought by saying that the theory or the vision of it remains very much alive. So I like to think the same thing. And I will end on that note. So again, this is, I guess, in my thumbnail image, this is an equation for quantum gravity, and I just simplified a bit more. We got rid of Coulomb's constant, and I'm showing you the electric permeability here. But again, I'd like to hear any of your thoughts and comments, or if you have more information or thoughts, please feel free to email me. Thanks for your time.